Hi, this is Mark Roth, and this is Mathematics for Social Justice. So today I'm going to show you a game that I've been playing with my students at Tessellation School, but I learned it originally from Nicholas Branca, who was a math education professor from San Diego. So basically, I put my finger in this, I call it the yellow room. And I ask the students to tell me either to stay in the yellow room or to move to a different room. So if the students tell me to go to the red room, I say, okay, if I'm in the yellow room and you tell me to go to the red room, I go to the red room. And then, tell me to go somewhere else. So they say, well, or you can tell me to stay in the red room. Well, if they tell me to stay in the red room, I go back to the yellow room. Now, if they ask me to go to the green room, I go to the green room. Now, if they ask me to go to the blue room, I go to the red room. And if they ask me to go to the green room, I go to the blue room. If they ask me to stay in the blue room, I go to the yellow room. So they're supposed to keep playing the game until somebody can come up and do exactly what I do the same way I do it. This is based on a group from group theory called the Klein-4 group. And I think I've seen the letter V used for this group. But basically, the way it works is this is actually the identity element. So when you're told to go to the yellow room, you don't move. So if you're here and you're told to stay in the yellow room, you stay. If you're here and you're told to go to the yellow room, you don't move. Or if you're here, you don't move. Or if you're here, you don't move. Basically what happens is these three, if you're told to go from one of them to a second one, you go to the third one. And if you're told to stay where you are, you always go to the yellow room. So if you're in the yellow room and you're told to stay in the yellow room, you stay there. If you're in the red room and you're told to stay in the red room, you go to the yellow room. And the same thing for the green room. If you're told to stay there, you go to the yellow room. If you're in the blue room, you're told to stay there, you go to the yellow room. So basically we have yellow being the identity element, and R, we can write it like this, R squared. That means you're in the red room, you're told to stay there. That's equal to and if you're in the red room and you're told to go to the blue room, you go to the green room. And if red room, green room, in either order, you go to the blue room. And if it's blue room, green room, either order, you go to the red room. So actually this is a commutative group or an abelian group, which basically means RB is the same as BR, etc. for any pair. Now another way to think about it is, suppose we have an axis here. So this would be like actually the vertical axis. So being told to go to the red room is like flipping the square that would take you, across this axis, and it'd take you from yellow to red or from red to yellow. So if you're here and you're told to go to the red room, you go here. If you're here, you're told to stay in the red room, you go here. And if you're in the blue room and you're told to go to the red room, you go here. If you're here and you're told to go to the red room, you go here. We can think of this as a symmetry, where you pick up the square and you move it and put it back down in a different orientation. Anytime you're told to go to the yellow room, this doesn't move. Now, if you're told to go to the blue room, you flip across the horizontal axis. So if you're in the yellow room, you're told to go to the blue room, you go there. And if you're in the blue room, you're told to stay there, you go back. And if you're here, you're told to go to the blue room, you go here. And if you're here, you're told to go to the blue room, you go here. Now, finally, what happens when you go to the green room? You do a 180-degree rotation around this center point. So if you're here, you're told to go to the green room, you go. If you're here, you're told to stay in the green room, you go back. If you're in the red room and you're told to go to the green room, you go here. And if you're here and you're told to go to the green room, you go back. One way to actually sort of make this fun for a class is have all the students go outside and have a big square on the ground. Maybe it'd be, the cracks from a sidewalk, I don't know, but a big area for like part of a class. My class size is only 11 or 12 or 13, but I'll have say half the students here and half the students here. And I said, okay, now go to the red room. So that would send these students here and send these students here. And they say, now go to blue room. That would send these students here. And if there's students here, they go here. And if I say go to the green room, they would switch, or like this or like this. You can actually do this as young as kindergarten, actually. You know, a student can sort of get a lot of recognition by being the first one that can go to the board and do everything the same way I do. Another way to do it would be, we can do it where we add mod 2 coordinate-wise. If you're here and you're told to go here, you actually add these coordinate-wise, and you do it mod 2. So mod 2 means you're working on a clock with two numbers. So you have 0 and 1. So on this clock, when you add 0 and 0, you stay here and don't move, so you stay on 0. 0 plus 1, you would start here and go 1 and land on 1. And 1 plus 0, you'd start here and not move, so you'd land on 1. And 1 plus 1 means you start on 1 and go one space, you land on 0. When you add this and this coordinate-wise, 0 plus 0 is 0, and 0 plus 1 is 1. So when you add this and this, you get this. So if you're here and you're told to go to, if you're in room 00 and you're told to go to room 01, you go over there. Now if you're here and you're told to stay there, when you add coordinate-wise, 1 plus 1 is 0, so you go back to here, and so forth. So that's another way to do it. You can also do it with matrices. So we can multiply matrices. And so suppose I'm here and I'm told to go here, I would multiply these two matrices. And matrix multiplication isn't always commutative, but I believe it is in this case. So if we put these side by side and I multiply, so I kind of think of it like this being raised up. And so I want to see where this and this intersect right there. I'm timesing this times this, and then I'm adding this times this. So -1 times -1 is +1. And to get this spot, I kind of times this, and I land there. So it's -1 times 0, and 0 times -1 is 0. Then to get that spot, I times like this and down here. So it'd be 0 times -1 and 1 times 0. That would be 0. For this spot, I'm going to go this times this. So it's 0 times 0 plus 1 times -1 is -1. So this is my answer. So notice when I times these two, I land there. So again, this is another way to get the Klein 4 group. So the previous example was the Klein 4 group, and the group has, we say, order 4, which means the set has cardinality 4. So actually, there's a second group that has order 4. It's the cyclic group, and so we can play the same game, but the rules are slightly changed. So if you're in the yellow room and you're told to go to the red room, you go again. But then if you're told to stay in the red room, instead of going back to the yellow room, you go to the green room. And if you're here and you're told to go to the red room again, as before, you would go to the blue room. But now if you're in the blue room and you're told to go to the red room, instead of going to the green room, you go to the yellow room. So what's happening is you're basically rotating counterclockwise. So if I'm here and you tell me to go to the red room, I go. If you tell me to stay in the red room, I go here. If you tell me to go to the red room again, I go here. And if you tell me to go to the red room, I go here. Now, if you tell me to go to the blue room, I go here. If you tell me to go to the blue room again, I go here. And then blue room again, I go here. And blue room, I go here. So going to the blue room rotates you counterclockwise, where this time I was moving clockwise. And like before, being told to go to the green room is a 180-degree rotation around the center. If you're told to stay in the green room, you go here. If you're here and you're told to go to the green room, you go here. And green room takes you from here to here and from here to here. So that doesn't change. So that's another version of the game. So another way to show these games is on a mod clock. So if we have mod 8, we have 0 at the top and 4 on the bottom and 1, 2, and 3 on the side and 5, 6, and 7 on the side. Let's call this yellow and call this red. Maybe we'll call this green. Call this blue. So we can show this to students. So if I'm in the yellow room and you tell me to go to the red room, I just multiply 1 times 3 and I get 3. So I go to the, if I'm in the yellow room and you tell me to go to the red room, I do go to the red room. Well, what happens if you tell me to stay in the red room? Then I go 3 times 3 is 9. So I start at 0, and when I go 9, first I go 8 plus 1 is 9. So if I'm in the red room, you tell me to stay in the red room, I go to the yellow room. Well, suppose I'm in the red room and you tell me to go to the green room. Well, 3 times 5 is 15. So I start here and I go 8, 16, back up to 15. So if I'm in the red room and you tell me to go to the green room, I go to the blue room. Suppose I'm in the blue room, you tell me to stay in the blue room. 7 times 7 is 49. So I go around 8, 16, 24, 32, 40, 48, 49. So if I'm in the blue room, you tell me to stay in the blue room, I go to the yellow room. If I'm in the blue room, you tell me to go to the green room, 7 times 5 is 35. So I go 8, 16, 24, 32, 33, 34, 35. So blue room to green room sends me to the red room. So this again is the Klein 4 group. Now I have to change the clock to do the cyclic group. So this time I can use mod 10. This is the other group. It actually has a cyclic structure. And if I times by red, it'll get me all the way around. So if I'm in the red room and you tell me to stay in the red room, 3 times 3 is 9. It takes me to the green room. And if I'm in the green room and you tell me to go to the red room, I go 3 times 9 is 27, which is equal to 7, mod 10. And then if I'm at the blue room and you tell me to go to the red room, 3 times 7 is 21, which takes me to yellow. So I cycle around the squares counterclockwise. Well, when I was using this other picture, times going to the red room, the red room, the red room, and the red room had a cyclic structure. So let's look at a few other things. If I'm in the blue room and you tell me to stay in the blue room, 7 times 7 is 49. It takes me to the green room. If you tell me to go to the blue room again, 7 times 9 is 63. It takes me to the red room. And now suppose I'm in the red room, you tell me to go to the yellow room. Well, I stay in the red room because 3 times 1 is 3. And suppose I'm in the green room and you tell me to stay in the green room. I go to the yellow room because 9 times 9 is 81. And if I'm in the blue room, you tell me to stay in the blue room. This time I don't go to the yellow room, I go to the green room because 7 times 7 is 49. It would take me there. You know, students can go to the board and do this on the board. Another idea would be having 6 rooms. And this time we're actually working mod 9. Now when you multiply mod 9, a quick way to do it is to add your digits, find the digit sum. So if you want to go like 4 times 5, you would get 20, but that's equal to 2 mod 9. You would just add 2 and 0. If I'm in room 1 and you tell me to go to room 2, 1 times 2 is 2, I go to room 2. But if you tell me to stay in room 2, 2 times 2 is 4. I go to room 4. Now suppose you tell me to go to room 5. 4 times 5 is 20, and we already saw that takes you to 2. If I'm in room 2, you tell me to go to room 8. 2 times 8 is 16. I add 1 and 6, and I go to room 7. If I'm in room 7 and you tell me to stay in room 7, 7 times 7 is 49. I'm working mod 9, and so I can ignore the 9. It's equal to 0 on the mod 9 clock. So 49 just becomes 4. So 7 times 7 is 4. If I'm at 4 and you tell me to go to room 8, 4 times 8 is 32. I add the 3 and the 2 and go to 5. So this is another game you can play. And finally, you can play with a cube. So to set up the coordinates, to distinguish between this point and this point, I can call one point 0 and the other one 1. But if I also want to put coordinates here and here, if I just repeat the 0 and the 1, I can't distinguish between the two zeros or between the two 1s. So I can put a 0 in front of both of these and a 1 in front of both of these. I can't distinguish, if I try to copy those up here, again, I can't distinguish. So I can put a 0 in front of all of these and a 1 in front of all of these. Suppose I'm at point 0, 1, 0, and you tell me to go to point 0, 1, 1. What I can do then is just add component-wise, mod 2, and that would take me to here. Now there's another way to think about it, which goes back to my first bead necklace video, where we made quadruples by slicing through the cube different ways. One way to slice through the cube was to do the 6 faces. So if you're here and you tell me to go here, I'm also including the origin. This would be the 4th point of the bottom. So if I'm here, you tell me to go to here, I go to here. Or else I can just add these two component-wise, mod 2. Suppose I'm here and you tell me to go to here. So that would be a way to slice through the cube. It would be this, 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 and this. I could slice diagonally through the cube. And so if you're here and you tell me to go to here, I go to here. Or again, I could just add component-wise. Another thing you can do is do a crisscross. So if I'm here and you tell me to go to here, this crisscrosses like that. So I would go to here. So again, we have 6 sides, 6 squares on the side of a cube, 6 diagonal slices, and 2 of these crisscrosses. So I consider this a crisscross. And then there's another crisscross like that. So that's another game you can play. You know, for the time being, that would be what I would use for a group. Yeah, if I want to go to a 2-operation structure, I can set something up like this, where I have a yellow room, a red room, and a blue room. And this time I'll be working mod 3, so I won't draw this for the students, but you can tell me to go to a room or tell me don't go to a room. So if you tell me to go to a room, I'm going to add. If you tell me don't go to the room, I'm going to multiply. Well, let me just write yellow here, red, and blue. So I'm here, you tell me to go to the red room, I'm going to add 0 and 1 and get 1. So I'm going to go there. Suppose I'm here and you tell me to stay there. Well, then 1 plus 1 is 2. So if I'm in the red room, you tell me to stay in the red room, I go to the blue room. And if I'm in the blue room and you tell me to go to the yellow room, I stay in the blue room because I'm adding 0. And if I'm in the red room, you tell me to go to the blue room, I add 1 plus 2 and get 0. So if I'm in the red room, you tell me to go to the blue room, I go to the yellow room. Now to multiply, if I'm in the red room and you tell me not to go to the blue room, that tells me to multiply 1 and 2. So 1 times 2 is 2. So if I'm in the red room, you tell me not to go to the blue room, I do go to the blue room. And if you tell me, if I'm in the blue room, you tell me, don't stay in the blue room, 2 times 2 is 4, which is equal to 1 mod 3. So if I'm in the blue room, you tell me, don't stay in the blue room, I go to the red room. If I'm in the red room, you tell me, don't stay in the red room. 1 times 1 is 1, so I do stay in the red room. And if I'm in the yellow room and you say, don't stay in the yellow room, 0 times 0 is 0, so I do stay in the yellow room. These are all different games that you can play that introduce different structures in abstract algebra.